Hello, everybody. We're here today to talk about the cloud. Hi, everybody. We're here today with Dr. Larry Dribin to talk about cloud computing. Dr. Dribin is a consultant and educator who assists organizations in understanding and adopting new technologies and new government regulations. His consulting firm, the Pearl Street Group, provides program and project management, process improvement, and measurement consulting services to both business and information technology organizations. Dr. Dribin is an adjunct professor at DePaul University, Chicago's College of Computers and Digital Media, where he teaches a variety of courses in cloud computing and software engineering. I've known Larry for a very long time. He's extremely knowledgeable about a wide range of technological subjects. We're very lucky to have him here today to talk about the cloud. Larry, thank you so much for your time.
Michael, thank you so much for having me. I really, actually, it brought back a lot of memories to focus on the cloud, not just currently, but to go back to talk about the beginnings a little bit based on your questions. And I'm looking forward to this.
Me too. So let's get started. Let's just dive right in. Simple question. Don't assume anything about our audience. Can you give us a simple explanation for what the cloud actually is?
Okay, but before I do that, I want to go back and get back to, I think, June of 2010. And I had never heard of the cloud. The cloud was out there. It was in its early infancy. And I went to a seminar and someone mentioned the cloud. And to me, it sounded, what is it? First thing, and sounded pretty neat. And so I started doing some research, and then I met another instructor at DePaul. We did some research. We said, wow, this is really something. And we approached our dean and said, let's create a course in cloud. Of course, while we did that, we had to contact a number of different vendors, other schools. University of Utah was one, I think, Illinois Institute of Technology, Illinois Tech, and see what they were doing. And we put together sort of our first cloud class, which we delivered that January. Since then, I've been heavily involved in teaching cloud. But in some ways, I'm very knowledgeable of the cloud. I wouldn't say I'd be the best cloud programmer. I think I've tried to take a little different approach. So we go back to say, what is the cloud? What sort of struck me as interesting back in 2010, and it's still interesting today, only many, many times more so. You have to, and I'm going to do this two ways. First, I'll talk about what it is, and then maybe we'll get into a little bit of how we got there from what we were doing, because I'm one of the, I think, children of the computer age. I was born there, and most of my career has been in some aspect of it. So the cloud is basically, it's a computer service that you get. That could be a search. It could be an application to order goods or services. Food, it could be hardware that you want to use, some kind of service that involves a computer. And that service is available on the internet. So I can get it literally from anywhere, any device, my phone, my desktop, my laptop. If I'm in work, from my work computer. So we've had that. It's a service. It's available via the internet. It's typically self-provisioned. That means I can set that up, my service myself. And going along with that, it's very flexible. There are a lot of different options in the way I do it. It's elastic, means it can grow and shrink. So if I think I have a service that I can have, let's say 100 people on a call like this, I can design it for 100. But if it's only 50, I can cut it back. And oftentimes I can save money by that elasticity, because it's oftentimes, it can be, and not always is, in most cases, it's not a pay-as-you-go model. We can take out our credit card or my credit card, or better, your credit card, Michael, and go on Amazon or Azure today and rent 1,000 computers for a half hour and do something with it and put it on your credit card and be done. And that would be, we've self-provisioned it, we've set them up, and we pay for them all on a credit card. But it's always very flexible because of that. And from the side of view, what's happened with the public cloud vendors, For all practical purposes, it's virtually limitless. Want 1,000 computers? How about 50,000? There's probably some limit where they'd like you to let them know a day or so ahead of time. But other than that, you could ask for almost as many as you can conceivably use, which gets to be important in certain kind of applications. So we talked about it being elastic, virtual, very flexible, easy to set up and self-provision. That's pretty much basically the cloud. There are other features that are available. It can provide high performance by harnessing 1,000 computers to do one task. It can provide high availability by configuring those computers in ways that even if you lose a computer or a number of computers or a whole data center, your application can still be up and running. And I think what's been happening now is that service could also be a database, a specialized database. It could be a health database, let's say version on anything. It could be a database of different happenings in terms of sales of goods and services. How many autos were sold this week? What regions? What kind of cars are people buying? So there's a lot of information out there that's available in the cloud.
When you say, I just wanted to ask a side question. You said that before we move on, you said that for all intents and purposes, that the cloud is limitless. How can anything be limitless? What gives it this limitless quality?
Well, I think the major cloud vendors have at their disposal literally millions of CPUs. And we'll get into that a little bit more. You know, I say virtually limitless. If they have 25 million CPUs and you want a job that requires 25 million CPUs, it's not limitless. But for most practical applications, you would never need 25 million CPUs. You'd need maybe 1,000, 2,000, 10,000, even for very large machine learning applications. So in that sense, it's limitless. And it's like, plumbing in a building. If everyone flushes their toilet at the same time, you're going to have a problem. Or if everyone turns on the hot water at the same time, it's a problem. But that's not the way it works. Typically, 5, 10, 20% of the people would be using something on the cloud. The rest of that is available for other people to use. And they design it for what they figured their peak usage. They're able, because it's a service that goes across the world, they can do a pretty good job of estimating that and balancing that.
So how did we actually get here? What has enabled the rise of the cloud? I know we've talked about how in the past, there was 60s and 70s, everything was about the mainframe, and then the 80s and 90s, you've had the client server kind of revolution. And then in the aughts and around 2010, the cloud emerged as the new paradigm. What technologically, what occurred that made this possible, that enabled it?
So I'm going to talk about it from two different points of view. From a very simple point of view first, and then get into some of the underlying technologies. So let's say in, trying to figure out what year it was. In the 1970s, I was working for a vendor. We had an application that we were selling to a number of different clients. This was a pharmaceutical application. And we had a number of sales going on at the same time, and a number of clients, and clients would have problems. And we had, I think, 3 computers they were using to do our development and testing on. And we had development tools, testing tools. But each time a customer came in with an issue, we had to stop and reconfigure the hardware, actually put boards in the computer, take boards out to represent their application, to either try to recreate their problem or to test a new feature that would only work on their system. So think about that. Between each use of the computer would be a half hour to an hour, and there was supposed to be, you always leave the computer as you got it, which people forget. which means more time to set up, which means you may run out of your testing time or whatever. So just think of that as the problem. We're getting swapping boards in and out, different kinds of drivers, different kind of printers, different kind of terminals. And that's the way it was. And that goes back onto when websites started coming up in the 90s. Still, most people had their own servers, very often on site. They'd buy a computer, put it on site, create, get a linkage to the internet and provide a web service. That quickly became a problem as a lot of these services were very popular. And so you may have 2 or 3 computers in your office, and by 4 o'clock in the afternoon, it's 110 degrees because their office wasn't designed for cooling. So, well, I got to go put in a data center. Well, in many cases, the actual data center for the company was full, or there were a lot of limitations on what you could put there. It was very difficult to do that. So companies came up and says, well, we'll provide data center capabilities. A warehouse with racks. You bring your computers there, we'll put them in there, and we'll maintain them for you to some extent. Oftentimes, though, the way the software was at that time in the early 90s, you had to have a console. You had to be there. Someone had to do there to be the work. Right around, I think it's 95 or 96, a company had this idea for virtualization. Now, virtualization was not a new idea. It was IBM and Burroughs were both using that in the 60s to simulate one computer on top of another. It was often a very difficult task to move from an old series computer to a new series computer. I think the IBM 7074, I think, was 36-bit, and the 360s were 32-bit, and you had to do some work to convert them over. So they created simulation programs called virtualizers that allowed one computer to be simulated on top of another. Okay, that was good. That was one of the key tools that allowed the cloud to happen. But let's go back to the story of the vendor. Now, typically, I have I'm a bigger vendor. I've got a lot of different clients. There's one company I work with. We had 90 different test stations in the basement. We had thousands of stores we had to work with. Each store had bought their own equipment. Sometimes we bought a chain that had totally different equipment than our standard. And so we had all of these different systems, and each one got very limited use. This one might be designed for a store in New York, and that store may not be needed for testing for weeks. And so it just sort of sat there. At the same time, I still had to do reconfiguring. 90 did not fit all 8,000 areas we were supporting. So I was still pulling boards out, putting boards in, moving printers, moving different devices, point of sales devices. Got very complex and difficult and expensive. Once virtualization came in, and these data centers were opening up where I could rent space in them and bring my servers there. First, I brought them to local ones. So there was one in Chicago right off the Edens, not the Edens, I forget what toll it was, that right off 294. There was a data center there. You go there, and there was racks, and the company I work with, rented, a couple of racks worth of space. We brought our servers in there. We set them up. We trained their staff to do backups, so we didn't have to be there every night. But very often, if we had a major update, we had to go in hands-on and get it done. Once virtualization came in, that changed everything. So by virtualization, there was a difference. I think the early PC designers didn't really know how to design, or chip designers didn't really know how to design chips. All the mainframes of the 60s from Burroughs, IBM, Honeywell had very powerful instruction sets that allowed for security and allowed for handling of what are called privileged instructions. So I could do something special. And that's really how I communicated with the operating system. So they not only built hardware, but they built the software to support it. Intel was just building hardware. And so they didn't really build in some of the tools needed for a modern operating system. What was clever about VMware is they did something sort of a similar to the way Elon Musk did. Let's use 1,000 batteries to power a car. Who would ever think of 1,000 AA batteries? But he did, and it worked. They did the same thing. They said, let's go through all of the code in the operating system, find every place they make a privileged instruction call, and instead put in, since there is no on an operating system, where would we like to put a privileged instruction call, and pull that out, put in our software, our VM software, to call the equivalent of a software privileged instruction.
Mhm.
Once I did that, I didn't have to be at the computer console anymore. I didn't have to be close to the computer at all. As long as I had an internet connection, and we did have internet in the 90s, I could now log onto my machine from remotely. I didn't have to go down to that data center off 294, which is one of our major highways. And they found, wow, that data center is actually very expensive. And to cost to get lease lines in to target the audience we wanted, they didn't have that. There would be an added cost. So guess what? We found a data center in California, close to where Microsoft and Amazon were using, that had much better connectivity and a data center much more suited to the kind of website we had. So we moved it there. We could never have moved it there without flying people back and forth or training somebody and having them stay there without virtualization. Now with virtualization, I had my server, I could boot it up, I could do all kinds of things with it. I couldn't move hardware around, but because of virtualization, I can in many cases simulate various hardware components, so I didn't have to have them there. And as virtualization got better and better, there was more simulation of different devices. From there, so now we're in the 90s. We've got a remote server, 2,000 miles from Chicago. We're managing it completely remotely, booting it up, configuring it, running applications on it. The next step, so virtualization was one. The other one was the dramatic cost decrease in price of computer hardware. Mainframe cost in 1965, 70, $500,000 to $1 million. And it had a very small memory. By 1990, that same CPU could have been got in the PC size for $1,000 with more memory and more disk capacity. So you have the disk capacity and price coming down, performance going up, and virtualization.
Mm-hmm.
Now a crude virtualization. But at the same time, a lot of the vendors, the mainframe vendors, were saying, well, sometimes people need more than our fastest computer. What do we do about it? So they started creating what they're called clustered operating systems. So I can now have 3 or 4 mainframes operating as one large mainframe from a batch stream point of view. I put jobs in, I get jobs done. The cluster says, you go here, this job goes here, this job goes here. One of them might be running a virtual terminal for virtual consoles, all working very well.
But
So
did they have to be co-located in the same space, or could they be distributed all over anywhere from virtualization companies like over the country?
Yes, initially they had to be co-located with very special cables. As they got better and better at it, now they could have, using fiber optics, they could be spent dozens of miles, hundreds of miles, thousands of miles away. And so that allowed a whole different kind of computing. But you had the virtualization, you had clustering, you had low-cost hardware, you had vendors already set up just to run servers. They just had racks, air conditioning, they bring in electricity from maybe a couple different drops. So if you lost one electricity drop from, let's say, your Edison provider, There was another one. They'd oftentimes have motor generators for critical applications. So if you lost electricity from Edison, you'd automatically go back to motor generators. So they were developing foolproof applications that most data centers didn't want to do for things like the web. They wanted to run payroll, they wanted to run general ledger, they wanted to run their manufacturing and explosions, the critical things to the business. And see, these were sort of extra that these weird guys in web development were using. But they needed the same capability. So that was going on at the same time. Another thing that happened at the same time is going back to the early days of PCs. People started writing software and selling it either directly or as open source. Open source got very popular. If you're in a key university, you'd oftentimes get involved in a open source project. I want to build an open source operating system, Linux. I want to build an open source game, Doom. These things were getting very, very popular. And with the open source software, along came open source virtualization. Now I didn't have to just be on a VMware system. I could take the open source and put it anywhere. Well, Amazon said, we've got a lot of ups and downs in our use of our servers for our own. We could take advantage of that because we have people running around managing these things. We can managing them remotely. This is great.
Wait, I'm sorry. Could you restate this? You said that because the software was open source,
right?
It could be modified or tweaked to run on other machines, on
Right.
any machine.
Well, depending, there's a lot of different open source licensing, but basically it's software that you use to do something. So I'll give you an example. When I started working at GT Electronics. We're making telephone switches. We wrote our own call processing software. Took over 200 man years, over six years of duration. A very costly thing. The average company's not going to go into that unless they're really in the telephone business. By 2000, there are open source call processing applications available, but that everything we did for either a modest price or for free. And so you or I could start our own telephone company, at least from a billing and practical point of view, by using open source software. There is open source software to mimic what VMware had done. And once it's available, it's not just the limitations of VMware was going to add in terms of capabilities, but this is now my software. I can do what I want with it per the limits of my open source agreement. I can change it, modify it, enhance it for my own purposes, and resell it.
Right.
This was a tremendous boon. So many applications, solutions became available. Now, there's one thing that happened that was a big thing. And we had constantly, every year, we've been following Moore's Law. Moore's Law, every year, 18 months, I think, computer power would double. And that was because we started off, I don't know if you've ever seen it, the first 40004 chip, that first microcomputer that Intel made, it was about this big. And, you could see the transistor sort of glued onto it. It was, they add more and more transistors, more and more capability. And as that happened, the one thing that we kept getting faster and faster, more often faster clocks. 1 million instructions a second, 2 million instructions a second, 100 million instructions a second, 1,000 million instructions a second. Now we're at 1 billion instructions a second. Now that kept going on till 2006. And we got to around 4 billion instructions a second. And we found something out the hard way. Two things happened. Electrons started operating under quantum laws versus the regular laws of physics.
Wow.
Instead of going around a wire, if you have a wire going from one part of your secret key or the other, a real tiny wire, instead of following that curve, which it did up to then, it would quantum tunnel right through, go straight. Well, that's a problem. Now my computer's not working right. And the worst case is it would start up by happening intermittently and then get very consistently intermittent bad. So he said, we've got this limit of 4 gigabytes a second. At the same time, as the transistors got smaller, they got hotter. And how do I dissipate all that heat from this little thing? We got into, liquid cooling, all kinds of things. But here we are today in 2022. What is that? 26 years later, or 16 years later. And what's the fastest computer you get? About 4 gigabytes a second. We really haven't figured out how to get over that. There are a few people who will overclock it to 5 under unusual circumstances, or if I, liquid cool it with liquid helium or something like that. But we're about 5. So
you're saying we're still capped out at 4 billion instructions per second?
Yes. So what did the vendors do? They still could shrink the dies, and instead of going faster, they had to be very careful that they didn't get into these quantum effects or generate too much heat. So it did is said, well, we'll put 2 computers on that same chip instead of.
Oh, this is brilliant. I see it now.
Okay, now, if we could do 2, the next iteration will do 4.
Right.
The one problem is there wasn't a lot of software to take advantage of that, other than this clustering software for mainframes. So what did the cloud vendors start doing, or the vendors that would become cloud vendors? They took a lot of this clustering software and jury-rigged it to use the multiple processors that were available on modern CPU chips.
And Amazon really did take the lead in this? Or were there other companies that we are not familiar with that they made?
It was the Amazon, Google were the ones at the time. I think Microsoft was there shortly thereafter. There is open source software for clustering. It's called Beowulf.
Mm-hmm.
Beowulf software. So I didn't have to create that myself. I could go get it, modify it, and then that's a good thing. The other thing that happened in 2006 is the hardware vendors finally figured out how to really design a computer. And by that, I mean, they actually added privileged instructions and security into the computer. So I didn't have to do things the VMware way of going through all the code in the operating system and pulling out places where I needed to. I could just use the privileged instructions, and they would trigger specialized interrupts to allow for automatic virtualization.
Well, they were probably responding to the market demand for that.
Oh, yes. And by that, I say they had a big demand for years. Why they never put in virtualization right away, I have no idea. Maybe it was much more harder than I think in software and hardware, but there really wasn't anything to run on. 2006, the world changed. And you'll see really around 2006 is when the cloud really start getting to be turned into the cloud, where you now had vendors that were saying, I've got all this capacity, Amazon for one. November, December, I need all these computers to handle my order volume and my scheduling volume. What do I do with it the rest of the year? I'd probably go from a 100% load down to 20% load in January, February. Why sit there? So some bright person at Amazon said, we could resell those computers. Everyone can now use virtualization. They don't care where the data center is. And that was Amazon was born.
So where actually is the cloud? I mean, where are these data centers? I mean, we hear about the cloud all the time, but we never really see it. Maybe we do know. Maybe we do see it.
Can I show you?
Sure, if you can. I suppose they're in warehouses all over the country, distributed across the various regions.
You've disabled the sharing, so.
Okay, sorry about that.
But what I was going to show you is an Amazon map, Google map, and a Microsoft map of where their servers are. And they're basically broken into regions and then what they call zones or availability zones and local zones. And they're everywhere. I think some of them, what was it, had 21 regions and 71 zones within those regions. But I think that may have been Google. But basically, they're putting them wherever there's a need. And the need may be usage or it may be regulatory. So in Europe, there's a general data protection regulation that says certain personalized data can never leave the country. So I can't have a server for a German healthcare system holding the data in France. It's got to be in Germany.
That's a very interesting requirement in a world that's so virtualized. It seems almost
No, there's a lot of privacy.
archaic. Yeah.
They're more into privacy and control of the data. They also say if you delete your data, it's deleted.
But can't you control privacy regardless of where the data is based?
We can't say that these regulators are always as up to date as we'd like them to think and globally.
Right.
The German regulator, I have my own view of the world and I want to keep German data there. And there's probably a substantial portion of German voters who want the same thing when they're told to ask for that by their politicians.
Mm-hmm. Right.
So, I mean, I'm sure it'd be the same for, Texas would not want most of its data managed in a data center in the blue Chicago, and vice versa.
I mean, from the story that you've told, which is great, by the way. I mean, I don't think I've ever heard a history of cloud computing like that, and that's certainly that little piece of information about the 4 gigabytes per second constraint is fascinating. I did not know that, and that explains the why they went big and they scaled, was because they couldn't get faster and they couldn't get smaller. But I mean, all of this sort of would suggest that the traditional data center is obsolete. Presumably it is. I mean, I remember when I first started working in this industry, there was, I can still remember the data center and the magnetic tapes, and it was air conditioned and, all the mainframes. But I mean, are there still businesses that have their own data centers and in which there's cases where it doesn't make sense for them to use the cloud, and that it makes sense for them to maintain their own data centers? I mean, as hard as that is for me to understand, I mean, is that something that's reasonable?
Well, I think absolutely. So there's still other issues. Just because I have these virtual servers, they still have to get data in them and out of them. And if I have to go from, let's say, Chicago to a server on the West Coast, it can take probably another 40, 50 milliseconds to get to the West Coast, versus if the data center was in Illinois. Different companies bought data centers. Another thing too, mainframes do things, they're designed for a different kind of workload than a PC. So we get these racks of PCs in the cloud vendors. I can configure them myself, but what I can't do is control their IO throughput. Mainframes are designed for very, very, very high-end data throughput. To and from the disk, everything probably is fiber connected. The top of the line of everything that your average cloud vendor doesn't have today, or they're getting there. So I think that's really key to say, in my mind, there's really a performance continuum. What do you need? From a handheld to a local server, to a regional server or data center, to a mainframe, to very specialized computers, whether they be quantum computers, graphic processing computers with GPUs, or computers designed specifically for machine learning. And I think the key is, what does your application need? And so I have the issue of getting data in and out of the cloud. If I take, and I have a computer with a 500 gigabyte disk, If I restore that to the cloud, it takes about 3 hours at my internet speed. And I have a pretty good internet speed from Comcast. One of the higher ones, not the highest. That's 3 hours. That's a long time. If I was in the data center, if I copied from one computer to another, it could probably be done in 20 minutes. So there's these issues with the cloud having to do with latency. It takes a long time to respond. There's limited bandwidth to get information out of the cloud. Sometimes it's cheaper if I have a large database to enter into the cloud. Instead of sending it over the internet, I'll take a dump of that database, put it on a 8-10 terabyte disk, and FedEx it to the cloud vendor, have them mount it on their system, and suck the data in that way because it's much faster.
So
including going through FedEx.
Are the cloud computing vendors doing anything to improve latency and bandwidth?
Well, they are, but I think you got to go back and say, what is the need for that? So yes, the cloud vendors have these very large, massive, with tens of thousands, in some cases now hundreds of thousands of processors. There may be 100,000 processors, each of which have 10 CPUs in them, on each chip. So now you have 100,000 processors times 10, you have 1 million compute units. So there's a huge amount of power there. They're always trying to stay ahead of the curve. But latency, as I go further away from the cloud, is a problem in some cases, but not in every case. And I think that's the key. So we'll make us say what the cloud vendors are doing is what they're calling edge computing. They're taking part of the cloud, a number of processors and memory, sort of like a mini cloud, and moving that closer to the user in two ways. They're either moving it on premise. So if I'm a big vendor, whether it's CAI or whatever, Kroger, some of the really big vendors, that makes sense to actually put that portion of the cloud in their data center because they can get quick access to it. Or they're putting it in telecom companies. So where the leased lines, or not the lead lines, your internet lines come in to be serviced before they go anywhere else for another hop. Every time I do a hop on the internet from one computer to another one router to another, that's 10, 20 milliseconds. And that's noticeable to the human eye. That's the problem. So typically, I think the average connectivity between you and the server you want to get to is about 80 milliseconds. That's less than a tenth of a second, but you can notice it. So to cut all those hops down, there may be 7 or 8 hops. We'll put a part of our cloud right in your facility, or part of your cloud right in the telecom, your AT&T center, or your whatever you have for your.
Is this what they mean by hybrid computing?
No,
that's a totally different concept. Yeah. What you were talking about the 1 million CPUs. You're talking about
1 million compute units.
Yeah, we also see GPUs mentioned a lot in reference to cloud computing. What is the difference between the CPU and the GPU, and why are GPUs becoming more important in cloud computing?
CPUs are general purpose computers. They do load, store, add, subtract, multiply, divide. That's about it. Some of them have some additional higher level instructions that can do some aspects of matrix multiplication, but they're more or less general. Certain applications require a lot of matrix operations, adding columns of numbers together, multiplying two matrices by another. I may have a raw data value and I may have a value I have to adjust it for. This is very big in any kind of video. I need to adjust the colors. I need to adjust the shading. How can, if I did a simulation, like in a game, how do I have the light coming from behind the guy who's doing the shooting. And then as he turns over to the side, looking sideways, the light is now shining on him differently, and the left side of his face is in shadow. And he further turns, his head is in shadow and his face is brightly lit. That's all done using matrix mathematics. In order to do that, particularly for graphics, they created graphic processing units, specialized devices that are not good at general purpose computing, but very, very good at doing matrix operations. Those matrix operations, they could be 100 to 1,000 times faster for the same amount of computer hardware, because they're very specialized for that one purpose. They started off as they sound, graphic processing units. But smart developers thought, wow, I could use that power for something else. I could use that power to maybe evaluate a computer-aided tomography graph. Or I can use that to better compute the orbit of where the James Webb telescope is going to be on March 15th. As they started using it for other purposes, some of those purposes got very popular. The first one is really crypto. Bitcoin and their proof of work algorithm requires you do a lot of computations to solve a mathematical problem. And if you solve that problem before anyone else, you get a reward today of 6.25 Bitcoins, which is around $250,000. If I want to be a Bitcoin miner, $250,000 is very enticing. I need to be able to do a lot of these operations. If I go buy a GPU, I can speed up my computer 100 times in solving the problem. So if I get there first, I'm going to get that 250,000 more than anyone else. So they started using GPUs to solve the Bitcoin hashing problem. In addition, though, there are a lot of other people, weather predictors using, we can use GPUs to do the math, figure out if it's going to rain tomorrow. We can use GPUs, certainly the shading and gaming, but more and more people came up with uses for it, and they're very, very popular. If you look at anyone, a university that has a high performance computing center, they probably have a relatively large processor with 100, 200, 300 processors, maybe 1,000, and 1 or 2 GPUs to speed up processing. That was the other thing that really started happening in the 2016, 15, 16 range. We had GPUs. We had spent from 2006 to those 10 years figuring out algorithms to write parallel programs to take advantage of all these computers by breaking a problem up into little bits and running it together. And using clustering, we could combine the results of many different computers working on the problem to get a total solution. So now we started really getting what I think is what the cloud is starting to look like today. I can distribute an application automatically to solve a particular kind of problem. Now, going back to the edge, does every problem need low latency? No. If I have a machine learning problem that's going to run for 2 days on 2,000 computers and 2 GPUs, it's going to run for 2 days and 2,000, 2 days. I don't need low latency during those 2,000 days. Where I need low latency is when I have to get data in or out of the computer quickly to respond to something, typically real time. There's talk, self-driving cars will take advantage of that. I don't think that's going to happen for a long time because no one's designing to that criteria. Everyone feels to now and a long time in the future, we're never going to have low latency everywhere.
Right.
and may not even have interconnectivity. It wasn't that long ago, I was in Phoenix and I was taking a drive up to the mountains to Sonoma, and I had a conference call. I said, no problem, I'll just dial in. Well, wait a second there. Dial in. There is no internet service in vast parts of the mountain area. Now, I never thought that on an internet, they would, on an interstate highway, a major interstate highway, between Las Vegas and Phoenix, I think, it would ever cut out internet service, a part of it. But it wasn't there for major parts of it, miles at a time. So I think till we get really high speed internet connectivity everywhere, people aren't even going to try.
They're not going to try what?
Having cars controlled by a central AI.
Right, right.
The FCC, they've had this problem with 3G and airline altimeters. There also is another area where there's an area called vehicle-to-vehicle communications, where vehicles will communicate with each other and say, hey, there's a car ahead, he's got a problem, I better watch and avoid it. They actually cut down the bandwidth available for that to build a bigger block between that and some other applications. So,
well, what's a use case where edge computing makes sense?
There are probably a lot of use cases, but you got to be very careful. I hear the president of Siemens talk about that. They build a lot of the 5G equipment. That they're one of the 3 5G players. And someone asked him, what's the best use case? And I was very surprised. I thought it'd be some clever health thing or what. It's a gaming. If I am doing a web-based game with hundreds of other players,
right,
I can't afford 10-second, millisecond loss in latency.
So that's more important than people in their cars, in self-driving cars, right?
For right now. I mean, eventually, there's no question they'll all be connected. But then eventually, I don't know if it's 10 years or 30 years or 50 years. Mm-hmm. The 5G rollout itself is going to be, $2 trillion that you and I are going to have to pay for. And that's probably not going to give you the kind of ubiquitous 5G everywhere. That mountain road I was on and in Phoenix may have internet now, but it may not have 5G for another 10 years.
I want to take a quick pause to read a word from our sponsor. We're sponsored today by True Project. True Project is a management, control, and oversight solution, software as a service, that is designed to monitor all of an organization's projects all the time. True Project protects organizations from troubled project and failure issues. Some projects go awry with significant consequences, and a percentage of projects will have modest to intermediate problems that will grow into more significant issues if not identified early. It is critical to minimize these situations and to get as early a warning as possible regarding issues that management should be alerted to. The goal of True Project is to provide continuous oversight and governance of each project and to alert management to those projects requiring attention. With oversight provided by True Project, you will reduce project failure, reduce costs, and achieve greater management insight. If you're interested in this, you can find out more at www.trueprojectinsight.com. Thank you. And now back to Dr. Dribin. Larry, let's take a quick change of direction here. We were talking the other day about some of the more well-known services that are provided by the cloud, infrastructure as a service, platform as a service, software as a service. And you had mentioned that there were upwards of 300 different types of services that are provided from the cloud. Could you give me an idea? Could you give us an idea of sort of the range and scope of these beyond what we might the more common ones that we're familiar with?
Well, for one, there's a bunch of public databases that are available. There are a bunch of private databases, let's say MySQL, whatever, that I can use. So now it's more than just here's a computer. Now it's here's a computer pre-configured with a variety of applications on it. It could be Office 365. It could be an SAP application. It could be anything. The key is that the vendors have gotten into whatever they can configure it in a way to sell, they will, however they monetize it. So there are all these services out there. When we started talking about cloud, I think Amazon had 8 or 9 different services. You could rent a disk, you could rent a computer, a couple of different kinds. Now you can rent any kind of, you want a Mac, got it. You want a PC, you got it. What kind, how many, how fast, how many processors, how much disk, how much cache, how many GPUs, what kind of GPUs. In addition, what kind of databases. Plus, there are an awful lot of pre-configured applications. One of the things, we're also constantly improving. So VM was a major improvement over doing it the hard way, wiring, boards together in a frame, which I've done all too many times. It's a lot easier to just write the software and say, oh, but VMs still have a problem. How long does it take for you to boot up your machine? Maybe 20 seconds, much better than it was 2 years ago. Still 20 seconds. How much work do you have to do to build your own computer? You got to put in an operating system. You got to add the users. You got to then add the applications and the databases and make sure that all works. Maybe that computer is always also getting data from another computer, so you got to work on that. And it becomes a big configuration issue for the sysadmin. Takes days to weeks. So another little company came along and says, oh, we can, if we standardize all that and use something, one of the operating system features, we don't need to create a whole VM. We just need to create the shell of the VM and run it in a VM. And that shell of a VM is called a container. So where may take 20 seconds or more to start up a VM, a brand new machine, to boot it up and get it running, probably more than 20 seconds. I can start up a container in a couple seconds.
Got it.
And the containers, where with VM, now I could configure a computer and in software, move it somewhere else. I still had to do a lot of configuring. What database, what operating system, how much users are going to get. Each time I had to recreate that. I could move VMs pretty easily, but with containers, they also said, well, let's standardize on our configurations. So now I have very standard configurations that allow me to move an application much easier than a VM. And that's a Docker container. Docker's the company that came up with it, and they're still the leaders. Now I have a Docker container, which is a CPU and application database, all bundled together, and I can move it around and duplicate it and triplicate it. And if I want more of them, I just create more. They're now, in a sense, CPU independent. I don't have to assign a Docker to a CPU. I have them available, and the CPUs can operate them as they get to them, more or less. So now I need something to orchestrate all those containers. If I have a lot of containers, and by a lot, dozens, hundreds. And so Docker came up with its own Docker convention for doing that. But an open source project from MIT called Kubernetes came up with a competing version. And guess which one won? Kubernetes. So now I will set up a system with dozens of Docker containers running as under a VM on X number of computer hardware nodes with X number of compute engines in the node and GPUs and data, and coordinate that all with Kubernetes. Life gets easier and easier for the sysadmins. They can do more and more things. Now, as life gets easier, we doing more things. Other things get more complex. Maybe I want to add in a machine learning element to it. So now I have to add that, but that can be in a Docker container, and it can be pre-configured. There's libraries of containers that can do all kinds of things off the shelf, sort of like pre-configured open source programs. So this is great because I'm now able to reduce the cost of computing another maybe order of magnitude.
Would you say that, I mean, is it fair to say that there is now such a thing as machine learning as a service, that a lot of these models, these machine learning models can be tapped into directly from the cloud? I mean, granted with some degree.
I would say there is without, I'm going to say this without a heavy proof. And the reason I say that, I started to look into that and I just never got to finish. But yes, you can get pre-configured models, pre-configured data, all kinds of things in typically Docker containers that I can then assemble to create a particular kind of solution that I now run my data through to get the machine learning.
And would you be able to, would you say the same thing about neural nets and about?
Well, I was just going to go there. So in order to do this, these models, typically a lot of them are using neural networks. So what are neural networks? They try to simulate a neuron. A neuron has many interconnections to other neurons. So they're feeding it information and they're providing information, and the neurons themselves somehow solve problems. So we have to create the same kind of environment where we have many. Just look at CPUs for a second. Regardless of on their own, they're in a Docker container or whatever. I need to design multiple CPUs that talk to each other and pass data back and forth. And as I pass data through them, they're going to be looking for something. What machine learning is best at, and I think we have to be careful here what it's good at and what it's not, is pattern recognition. So if they see a pattern that they recognize, that's a good thing. And they are very good at that, much better than you or I. As I pass that pattern through successively times, which they do automatically, they get better and better. So if I, let's say, have this shape bottle, and they first pass it through, they may say, oh, here's part of the edge of the bottle, and here's nothing. And then I say, okay, now here's the lip of the bottle, and they start seeing more and more details as they keep successively running through the data, running it through the neural net. The neural net has many different layers to it. Each net is taking data from the prior net, assimilating it, and trying to make a finer prediction. So what I'm really doing is I assume here are 200 computers in one level, 200 computers in another. The level one will send data to the level two that it will use as parameters to do a similar kind of analysis. And basically, they're looking for points of light or dark. And as they do that, they can slowly, as they go through level by level, they'll start out as, sort of like in the beginning, there was nothing, then there was heaven, and then there was earth. Right now there's black and white. The next pass, now we start seeing a little bit of a very rough shape. The next pass, the shape gets a little clearer. The next pass, and the passes are being done automatically by the neural net, not by you or I programming.
But we did talk about this the other day, and you said that there is for users to tap into the cloud in order to access for the cloud's neural nets. There's a fair amount of configuration that needs to be done from the user perspective, and maybe you could speak to that.
So yeah, I'm saying that there are, if you go to, and I was just on, in fact, I think I may still have it, they had a whole list of where it is, but services available. This isn't it, but there are a lot of pre-configured models available. Now that may fit your problem, may not. That's the key. The hard part is creating these models. So when I create my neural net, I have to say, these CPUs are in level 1, these are level 2, these are level 3, and they're passing data to each other. But not just passing data, there's also a feedback loop. They're getting data back from it. And what they're passing is really parameters. And so level 1 adjusts the parameters to level 2 adjusts the parameters to level 3. When they get to the bottom, they'll say, okay, here's the parameters why don't you start with these in level 1, and we'll get a more accurate picture. And eventually you'll get a solution that doesn't get any better.
Mhm.
Those are pre-configured, so I can go and get it. Will they solve your problem in machine learning? Don't know. One of the things we found is there's a lot of unknowns, is we don't know how these neural nets oftentimes solve the problem. They know they solve it. We couldn't write down the rules for that. In fact, there's a lot of work going on in AI right now called explainable AI. What are the rules that the AI created to go from point A to point B? How did they figure out this was a bottle? Sometimes we know, sometimes we don't. Sometimes these models are overly trained. As long as I hold the bottle up just like this, they can find it.
Mhm.
But if I turn the bottle this way, or if I add a pencil in a bottle, and suddenly now it comes up not as a bottle, but a horse. And they don't know why.
Well, this is a whole nother presentation, which it has to do with the fact that as our society is going to become, increasingly reliant on AI and on deep learning in particular, where nobody understands how the AI came to its conclusions, there's a great deal of risk in terms of, it coming to the wrong conclusions and nobody being able to prove that it was wrong or why. I mean, all it would take, think about fraud detection, think about people being imprisoned, arrested for, incorrectly. And there's people being dinged for insurance fraud. There are all kinds of patterns that could be misread, but I don't want to get into that because that's a whole nother long discussion. But what I am interested in, and what just kind of piqued my interest, was that from what I understand about deep learning in particular, AI in general, but deep learning in particular, is that it requires two things to get better and better and better. And it requires two things to continue advancing. One is extremely large data sets, and the second is large amounts of computing power. And it seems like we have both of those things in the cloud. By its very nature, we have enormous amounts of computing power that we don't have anywhere else, and we have enormous data sets that we do not have anywhere else. So it would stand to reason that there must be a large amount of deep learning research being done in the cloud computing community with the tools that they have. Are they perhaps running their computing power against their data sets, looking for patterns that perhaps no user, no client may be interested in? I mean, are they running experiments themselves in order to
absolutely
enhance deep learning?
Absolutely. Now, if I happen to be at a high-end school that has their own high-performance computer that they got on grant from whatever, that has 2 or 3 GPUs in it, I may not need to use the cloud. It may be too expensive. So there's a cost issue there. These models are not cheap to run.
Mm-hmm.
And to get 1,000 computers to run on a problem for a couple of days is not cheap. So someone has to pay for it.
But can you access general data, not necessarily your own data? In other words, if you...
Well, that's where I was going to go to next. So the key now is you need 2 things: a model that takes data and transforms it in some way to identify a pattern.
Mm-hmm.
And then you need the data.
Mm-hmm.
Not data that I own.
Right.
I may have some of the data in my computer. I may have some of the data in your computer, and your computer is in the cloud, and my computer is in the cloud, but yours is in Azure, and mine is in Amazon. Well, now I have to really get clever writing Azure code and Amazon code. And now I really double or triple the complexity of my problem to combine your data with my data. So that's another thing that's going on right now in the cloud, is inter-cloud connectivity.
Mm-hmm.
So I can use the same API to get your data as my data. read record versus read Amazon record, read Azure record with this, and this options. And that's going to be, I think, the next major area of improvement, because there's so much data in the public cloud and in various private clouds that it's not going to be, oh, I can do this all on my own. You're going to have to use data from many different sources.
So you think, I mean, there are privacy issues, obviously, but I'm assuming some of this data is going to not be bound by restrictions. It seems like we get to a point where we can rent data in order to develop more finely tuned AI models that we will, if we need large data sets that we don't have on our own, that is it possible that we'd be renting data?
Well, I think that's done today in many cases.
Okay.
I think there's going to be even more of it as we have something. We need some data that we don't have.
Mm-hmm.
That there'll be someone saying, "Okay, I can build that, and I'll sell it to you."
Mm-hmm.
We're seeing that. I think this is a key thing when we talk about competition with China. This is a big area of differentiation we have to be very knowledgeable of and careful how we manage. The Chinese economy is much more autocratic than ours. And they've much less of a concern about personal freedom and personal rights. And the Chinese people have been brought up with this feeling for a long time. So they're much more open to have their data owned and shared with the government or with different companies than we are here. That the Chinese entrepreneurs in AI say that difference alone is going to allow them to beat us in the AI market because they can get at more data, easier data than we will ever do because of our individual personal freedom and regulations around data. I have no idea whether that's going to play out or not. I'm telling you the point of view of the Chinese entrepreneurs that they feel they have a major advantage over us. And
I think they do. I think you're right. There was a Frontline documentary that famously stated that China is data is the new oil, and that China is the new Saudi Arabia, and that with the combination of their autocratic political structure and the enormous population and the amount of surveillance that they have, they are collecting continuous data on everything, and nothing stands in their way in terms of running models and computing power against that in order to advance their AI insights and their deep learning insights. So
that's the sort of standard story. What I don't think we don't know is just because you have a lot of data, if you have a lot of the wrong data, it doesn't help you very much. And I don't think we know going forward into the, further into the 22nd century, whatever century we're in, what data we're really going to need. They may have it, they may not. We just don't know. And I think that's the key, is we have to start having people get smarter in these models, better documenting, better understanding it, and gathering the right data to train the model. Mm-hmm. I said in one of our other talks that I thought Tesla's doing the right thing, because not only do they have their very big compute engines for MI in their cars, but they also realize that that's not the only kind of artificial intelligence you need. You need other kind of decision making. So currently the pattern recognition, and I think I mentioned this too before, we see a fire engine, I should have brought a little model one, in front of us, that's fine. But if we have the fire engine flipped over on its side, unless I've trained the model to understand that, in every possible way possible, it could be flipped over, I may never recognize that as a flipped over fire engine. And Tesla's had some problems where they've run into the vehicles on the side of the road that they didn't pick up as important, utility vehicles. So they understand that there's other elements to AI not related to machine learning. Machine learning does very poor at that. Machine learning does very poor at any kind of mathematical operation. that you and I may think of. They made great at math and at matrix multiplication and solving n-dimensional vector arrays, but they're simple. If you add 2 and 2, that's not the place you want to do that. You want to more go to your general purpose algorithm solver for that. And so that's combination. And I think we're still very early on in the model development. There's a lot more work that has to go into building good models, understanding deep fakes and how to identify them and prevent against them. And I think right now we're in an era, right now today, where who knows what we're going to see. We could easily see a deep fake of Putin saying something that he didn't really say. We could see a deep fake of Biden saying something he didn't really say, or Zelensky, or somebody else. So we'll see in the coming weeks real use of deep fakes in politics and in war, like we've never done before, as the hackers get up to understanding what's doing and are told what can they do to disrupt. So
this is turning into a discussion about AI, which is great, but I want to, as we close, to close this discussion, which has been very helpful for me, and I'm sure our audience as well. Perhaps you could give us some thoughts about the future of the cloud over the next, 5 to 10 years. And also, I'm just curious, what if we may have, related to that, if we have breakthroughs in computing power in terms of developing new computing paradigms that get us past this 4 gigabytes per second constraint, such as, quantum computing or 3-dimensional computing, biological computing. But I think quantum computing is the one that is the most realistic. And insofar as all the major cloud providers are developing quantum computers, they have them under development. It may not be a reality tomorrow, but they're making a big investment in that. That if we break past this 4 gigabyte per second constraint, what will that do to the cloud computing industry, which seems to be based on scaling up in order to compensate for that inability to get past that point? And also, what's just the future of the cloud in general over the next 5 to 10 years? What sort of changes do you think we'll be seeing?
Well, I think where appropriate, we're going to see more movement to the edge to get reduced latency for those applications that need it. We're probably going to see a lot of people moving to the edge that don't have to. And then after a while, things will stabilize and they'll go back and say, we don't need two microsecond access time. 80 is fine. But everyone's going to move to that right now. We want our own edge in our data center. So I think this understanding the computer curriculum continuum from mobile to the cloud and various bandwidths and latency along the way are going to be tailored to various problems. And we're going to get, I think, much better at that. I think the whole Internet of Things is huge as we connect more and more things to the cloud. Some need rapid response times, some don't. And how we handle all that and how we handle the data they aggregate. They may have more data in China about personal behavior, but we're probably going to have more data on IoT devices than they have that we collect for maybe smarter reasons. So, it's nothing is cast in stone. The whole area of the metaverse, we don't know what that's really going to be, but it's going to require the cloud to implement it. Without the cloud, there is no metaverse. You need this massive capability tying in with, enhancements in virtual device augmentation. You mentioned quantum computing. Until we figure out how to run quantum computers at something less than 285 degrees below 0 Celsius, at almost absolute zero, they're probably going to be in specialized data centers and will probably be available as a service on the cloud versus in your or my basement. We have the issue of latency. We have the issue of bandwidth. Security is an issue everywhere. And I think that's something that a lot of people don't understand. I saw one presentation you showed me yesterday. This is one of the people that are concerned about security in the cloud. In many places, the cloud is more secure than the average data center. So we really have to look at what aspects of security are there. The burden of security in the cloud is on the user, but this cloud data center as it is more secure than your average data center. They put tons of money, effort, time, training. They have man traps, all kinds of, one-way doors and things like that, that even no small data center has, and even a lot of big data centers don't have.
Have there been any in recent memory? Have there been any major outages or major hacks into the cloud that you can remember?
Well, there's been a lot of outages. Some usually self-imposed that an operator does something different and takes down maybe a whole availability zone. But no one has got into the cloud operating system yet. That doesn't mean they can't or won't. Mm-hmm. Sure, there are thousands of people trying, just like luckily there's been no major in any of our banking systems. If that happens, the world may be more changed than what's happening right now in Europe. If they took down the Fed, it doesn't have to be the cloud. If someone took down Amazon or Azure from the inside, it's certainly a possibility. There's a lot of attempts to prevent that, and smart vendors are going to start building applications that not only fit in different regions of the country and different data centers in the country, but different cloud providers. So let's say Amazon is hit. Is Azure also going to be hit? Mm-hmm. So if I really want to protect myself, that's the kind of thing we're going to want to look at, and people are doing. The other thing is right now, all of this is taking a huge, enormous amount of power consumption. And so how do we reduce that? There's all kind of efforts going into designing new chips, whatever. A lot of memory development chips are now putting microprocessors along with the memory, so we can do these massively parallel applications even faster than GPUs. I have no idea where it's going. We're stacking boards instead of horizontally 2, 3, 4, 6 high in terms of components. There's an awful lot happening right now that I think as we go there, there's going to be some movement back. I think, as you mentioned, vertical desktop integration. Getting your PC on instead of on your desktop in a server in your data center. There's always going to be give and take, but I think ultimately the key is going to be, where do you need the data to be, and how are you going to compute it? What kind of computing resources? And as we get better at that and more automated, certain applications, when you wouldn't use Siri on your phone, or as your Alexa, that's not being done on the device right then and there. That's going back to the cloud to do a lot of the heavy lifting. So I think we'll have to wait and see. But I think, to me, it's a very bright future. I think as we get more into AI, as we get into more autonomous vehicles, all kinds of anything, we're going to take advantage of the cloud in ways, and maybe this is the biggest, in ways we've never thought. When we had the first cell phones, they were actually phones. And then Apple came along and said, maybe you could do a little more than just a phone. And now 90% of my time on my phone is not using the phone, but all the other apps. That's in, 10 years? What's going to happen in the next 10 in the cloud? And it's not going to just be the cloud. It's the cloud, the handhelds. It's everything together is moving forward, and we're coming up with better architectures on how to integrate it together. So I think it's a fascinating opportunity. But in my mind, I think the cloud will be there for a very, very long time. It's sort of like, power. In the 1920s, a lot of people had their own power generation in the basement or heat. Then they got to, it's cheaper to have Edison do it, or whatever, your electric company. Now you can power your house by your truck. If you buy a Ford, Ford truck, or you can borrow a motor generator and power it. And if you got cheap gas, it may be close to the same as the electric company. So I think everything is in a massive flux of change, and that leads to tremendous opportunities. the cloud vendors are leading the way. They're making tons of money, and they have a lot of really, really good tech resources to try and figure out things. And I think everyone's going to get more and more into the cloud, even though they may do more processing on their phone.
Larry, always a pleasure to talk to you. I really enjoyed the time we got to spend today. I learned a lot. I hope you had fun.
Always.
And I'm sure our audience got a lot out of this. I hope we can have you back in the future to talk about additional topics. You're the gift that keeps on giving. And once again, thank you so much. And thank you to our audience for joining us today. We'll see you again at our next session.
Thank you, Michael, for inviting me, and good luck in this whole interview series. I think it's a great idea to get some people out there really talking about things from as honest and professional point of view as possible. There's a lot.
Thank you.
There's a lot of misinformation out there, and I think you're doing a good job in the area of technology to try and have people be there to try and shed some light on the truth.
Well, with that, I can't come up with a better closing remark than that. So thank you, everybody, and we'll see you next time.
Thank you, everybody.